The efficient exploitation of an electrically powered oil field requires optimizing the operation of its internal power distribution network. Medium voltage feeders in these networks are normally very long. Therefore, they are subject to significant voltage drops and undesirable losses, especially so when they are operated at or near full load conditions. Besides, modern electro-submersible pumps equipped with variable speed drives introduce harmonic disturbances which need to be mitigated in order to avoid damages to delicate control and protection electronic systems. All these problems can be solved reliably and cost-efficiently by installing reactive compensation systems and harmonic filters at selected nodes in the distribution network. Joint Operations, the binational oil company formed by Saudi Arabian Chevron and Kuwait Gulf Oil, recently asked Leyden to design a system that would enable them to take full advantage of the installed capacity of the existing medium voltage distribution system in the Wafra Oil Field in Kuwait, so that they could meet an aggressive production increase plan without installing additional feeders. Leyden accepted the challenge and devised a plan to study Wafra's power distribution system, which was organized in several stages. First, a field survey was carried out, collecting all relevant data about the distribution system itself, such as the characteristics of overhead lines, the type, size, and location of loads, as well as additional topographic data, single-line diagrams, and so on. Then, a large number of voltage, current, and harmonic distortion measurements were taken at selected nodes of the distribution network. This was done using power analyzers wired to the secondary windings of existing instrument transformers, but also by direct measurements taken on the medium voltage feeders. Measurements covered periods of time long enough so to identify all possible load conditions of the feeders. The next stage consisted in developing a computational model of Wafra's distribution system, based on a powerful simulation software package. Once the computational model was fine-tuned, current and forecasted load scenarios were selected for each of the medium voltage feeders. The optimum size, MVAR grading, and location of harmonic filters were chosen by using those configurations which minimize voltage drop and losses, gave power factor values closer to unity, avoided overcompensation, and reduced THD to acceptable values. Upon approval, Leyden prepared the detailed engineering documents for harmonic filter banks, including the electromechanical design and the power, protection, control, and communication circuits. Every piece of technical documentation, such as drawings, single-line diagrams, functional diagrams, calculation sheets, bills of equipment, technical data sheets, and so on, was subjected to prior approval by the end user before being released for construction. The extreme desert climate conditions at the erection site, with maximum temperatures reaching 60 degrees Celsius in summer and frequent sandstorms, called for the use of enclosures with an IP65 degree of protection. This was implemented by the use of standard 20 feet containers for 11 kV harmonic filter banks and 40 feet high-cube containers for 33 kV harmonic filter banks. The containers were conveniently adapted as mobile electrical rooms, adding access doors, complete thermal insulation, auxiliary voltage wiring, internal lighting, and a double air conditioning system, with one operating unit and one backup unit, each of them capable of evacuating the heat generated by equipment housed in the container, plus heat influx from the surroundings, even at maximum ambient temperature conditions. The use of containers as mobile electrical rooms also served the purpose of safely transporting factory-assembled harmonic filter banks over almost 15,000 kilometers, including several intermediate transshipments, so that the erection at the job site could be completed in a very short period of time and with a minimum of civil and electromechanical works involved. Harmonic filters were conceived with 3 stages in a 1-2-3 output ratio. For example, for the 33 kV filters, a 369 megavar sequence was chosen. Each stage is composed of laden environmentally compatible all-film capacitors impregnated with PCB-free biodegradable oil with internal fusing. Capacitors in each stage are connected in double Y with ungrounded neutral and are operated by a 3-pole vacuum circuit breaker which guarantees a restrike-free operation. The stage can be disconnected for maintenance by means of a 3-pole disconnector switch with 4-pole grounding blades. The filters are fitted with a mechanical interlocking system which assures that the disconnection and opening of equipment for inspection and maintenance are carried out under proper safety conditions for operators. Harmonic filter banks are protected against neutral unbalance, over and under voltage, overload, short circuit, and very high temperature in the mobile electrical room. Analog signals from primary elements, PTs, CTs, and thermocouples are digitized and fed into the control and protection PLC located in the local control panel. Local control panels of harmonic filter banks positioned throughout the oil field are connected by a radio link to a SCADA system in a central control room. The SCADA system allows to remotely monitoring all filter variables, which are represented graphically in a mimic diagram on the central control panel screen. The control system also carries a historical log of operation events and protection tripping. Harmonic filter banks can be operated either automatically or remotely from the central control room, according to load conditions in each of the distribution feeders. The control algorithm maximizes power factor and limits harmonic distortion on each feeder for any load condition. Harmonic filter banks were completely factory pre-assembled and tested under the supervision of a third-party inspector, Bureau Veritas International, before being released for shipment to the job site. Besides, all key components, such as capacitors, filter reactors, circuit breakers, disconnector switches, instrument transformers, and so on, were individually tested by independent inspectors. Some of the components were also type tested before approving their use in the filters. The adoption of standard containers as enclosures for harmonic filter banks simplified ocean transportation, since they occupy exactly the same space and can be loaded and unloaded in the same way as normal freight containers. Civil and electromechanical works were completed at the job site, while harmonic filter banks were being built at Leiden's factory in Argentina. Installation only required mounting equipment on concrete foundations, executing power and control wiring incomings, and closing radio links with the central control room. Thousands of dollars in commissioning and startup costs were so saved, and harmonic filter banks were made available for commercial use almost immediately after arriving in the oil field. Voltage, current, power factor, and harmonic distortion measurements taken after startup thoroughly confirmed the values predicted by the preliminary study made by Leiden's engineers. This demonstrated the advantages of designing reactive compensation equipment based on a previous system study, in terms of dollar savings and shorter lead times, as compared to traditional trial and error procedures. In this project, Leiden successfully put to trial all its capacities, interpreting end users' needs and expectations, surveying the job site, and collecting all relevant data for design, preparing a computational model of a power system and validating it on the basis of data collected at the site, designing the technical characteristics, size, and optimal location of equipment to be installed, constructing, assembling, and testing equipment according to end users' technical specifications and international standards, programming the most appropriate logistics, assisting locally the end user in the commissioning and startup of equipment, carrying out final field measurements to confirm that the project targets were achieved, preparing complete as-built documents, including operation, troubleshooting, and maintenance manuals, providing local training for end users' operation and maintenance staff, keeping reasonable flexibility all along the project to introduce changes in equipment design as required by the end user, providing permanent after-sales support. Leiden, 70 years building reactive compensation and harmonic filtering equipment for the improvement of power quality in low, medium, and high voltage systems.